Hi, I'm Minjong Yu. I'm PhD student at Sungkyunkwan University. Today, I'm presenting our paper, Model Adaptation for Time-Constrained Embodied Control. Let me introduce our CSI agent lab. Our lab, led by Professor Hong Woo, primarily focuses on training robust agents that can perform well in various environments and adapt quickly to new environment via reinforcement learning or imitation learning. Firstly, we conduct research on multitask and meta-reinforcement learning, aiming to develop RL algorithms that can quickly adapt to new tasks and perform various tasks. And we implement models capable of handling multimodal data such as images and language to train agents that operate robustly in diverse new environments. In case where data in the target environment is scarce, we focus on utilizing data from other environments. Also, we conduct research on offline reinforcement learning to achieve good performance even with limited data. Lastly, we are researching skill-based learning to train and perform complex and long-horizon tasks. We decompose tasks into round skills, enabling rapid adaptation to unseen tasks with minimal data. Here are some examples and demonstrations. We research training driving agents that can adapt to various environments or quickly adapt to new environments. Furthermore, we are researching methods to rapidly learn long horizon and complex tasks through skills, and to adapt unseen tasks by utilizing previously learned skills. I'd like to introduce the conference where our paper have been accepted. CVPR is an international conference on computer vision and pattern recognition, serving as a platform for researchers and industry professionals worldwide to present and share cutting-edge research findings and innovative technologies. CVPR covers a wide range of topics, including image processing, object recognition, and image segmentation, 3D modeling, and recognition and tracking. As one of the leading conferences in the field of computer vision, CVPR provides selected papers and diverse programs to offer important news and insights to experts in the field. So, from now, I'm presenting our paper, Model Adaptation for Time-Constrained Embodied Control. First, we explain the motivation for our study. Embodied agents, like home robots, are required to manage multiple control tasks. The image provided examples of these embodied control tasks in embodied environment. Additionally, in real-world contexts like autonomous driving, time constraints may arise. And the inference time vary due to differences in hardware specifications across different devices. Hence, it is crucial for an embodied agent operating in real-world conditions to adjust its actions according to both device specifications and time constraints. To solve this problem, we define the time-constrained embodied environment formally. Basically, we define multitask Markov decision process under time constraint. In this formalization, the reward function is influenced by whether there is a violation of constraint. And in a multitask setting, each task is represented by its own MDP, leading to the multitask environment being comprised of a collection of MDPs. This allows us to solve the environment problem by optimizing policy to control the improves time and performance according to tasks and constraints. Therefore, we proposed MODEC consisting of the three components to solve multitask and adapt to target device under time constraints. First, we use the base network for the purpose of solving a multitask control problem. This network is structured into modules, each containing a smaller network model designed to address the multitask environment by adjusting the path weights between modules based on the task. Additionally, by selectively employing part of each modules at inference, the model achieves dynamic adjustment of inference time. Next, the module selection network determines the optimal module combination of the base network based on the input resource utilization and task. This facilitates instance-wise computational adaptability by direct adjusting the modules used in the base network. Finally, the device adapter adapts the base network and module selection network to the time constraints of the target device. This network, trained with Fusion Learning, predicts an appropriate resource utilization that does not violate constraint as input it into the module selection network. In MODEC, first, we train the base network. This network adjusts the activation of modules according to the task through soft routing, using path weights computed by the routing network. It also has the flexibility to direct control inference time by using only part of modules for inference. In training, we use an algorithm for soft modularization, which adjusts weights for each task to regulate the running speed across tasks. And we train the iterative module selection network for selecting modules for base network. Determine the module selection is combinatorial optimization problem. This causes instability in learning performance due to very large action space. To solve this problem, we design an iterative module selection network that selects one module at each inference step and repeats this process for the number of modules to be used. Training the iterative module selection network leads to a performance decrease, attributed to the base network being originally trained the full set of modules rather than limited subset. To mitigate this problem, we jointly train the base network and the iterative module selection network simultaneously. Furthermore, the iterative module selection network is trained to infer actions as close as possible to actions using all modules, even when only a subset is utilized. To achieve this, we employ reinforcement learning to train both models and design the layered function to narrow the difference between the action using the current module selection and the action using all modules with each iteration. While iterative module selection network shows the improved performance, but the inference time overhead is excessive. Therefore, we train the single-step module selection network by utilizing the iterative module selection network as a teacher model. The objective of distillation is to minimize the difference of output values between the iterative module selection network and the module selection network, as detailed in the loss function. We train the module selection network by incorporating this loss in addition to reinforcement learning based on the rewards from the environment. The device adapter adjusts the pre-trained base network and the module selection network for various conditions of target devices and time constraints through fusion adaptation. To achieve this purpose, the device adapter maps the time constraints to appropriate number of modules to use. For training, we collect few-shot inference time data from the base network and module selection network on the target device. In experiment, we used 3 environments: MetaWorld, Kala, and AI tutor simulator. MetaWorld is a robot arm environment including various tasks like press button and open window and so on. We conduct both experiments on multitask setting and single task setting in this environment. Kala is autonomous driving simulator. We use several different maps to make multitask settings. And AI tutorial simulator is a home robot environment. In this environment, we experiment with rearrangement tasks for various object settings. The experiment table of MetaWorld and AI tutorial contains only results with a constraint violation ratio of less than 1%. In the Kala experiment, in contrast, we ignore the current action if constraint violation occurred and use the previous action again to make the violations affect the performance. In our experiments, we used 3 embedded devices: NVIDIA Jazz Orin, Xavier, and Nano. Among the 3 devices, the Nano has the lowest performance, while the Orin shows the best performance. All experiments include the result of inferences on these 3 devices. That model is deployed directly. First, we evaluated single task learning in the MetaWorld environment. In the given time constraint, our model demonstrated an about 25% performance improvement over the most competitive baseline D2NN. And we also evaluated multitask learning in the meta-world environment. In the given time constraint, our model demonstrates an 5.7% performance improvement over the most competitive baseline D2NN. These results indicate that our model achieves superior performance in the multitask robotic control with a time-constrained environment. And we evaluate autonomous driving performance in the color simulator. In the given time constraint, our model demonstrates an 14.4% performance improvement over the most competitive baseline DSNet. These results shows that our model achieved better performance in the real world, like driving environment. And the real world home robot scenario, we evaluate model and the baselines in the AI tutor simulator. In the given time constraint, our model demonstrated an 15.4% to 70.8% performance improvement for unseen tasks over DSNet. This result shows the robustness of our model in a real-world home robot scenario. Here, we perform the evaluation study for variants of our model. Model I in this figure, model I denotes a model variant without distillation. So it just use iterative module selection network, substitute module selection network. And model O denotes another variant directly runs the module selection network, so it doesn't run iterative module selection network. In this figure, model shows significantly outperform model I in terms of inference time, and also shows better overall performance compared to other models. This result demonstrates the superiority of the distillation method. In conclusion, we presented MODEC, which allows embodied agents to effectively adapt to time constraints on different target devices. Our model shows performance improvements of 25.1% and 5.7% respectively for single and multitask and meta-world. And in color, our model shows 13.4% improvement. Finally, in AI tutorial home robot environment, model shows a performance improvement of 15.4% to 70.8%. For future work, we plan to tackle the challenges of learning complex constraints from instructions, including safety and resource limitation. Thank you for listening our presentation.